So, okay, we should start the session now, and the recording has been started through OBS. Sorry for the last session. Actually, that recording was not audible, so I have make sure that it is not happening this time. So I think we should start the session. Yes. Okay. So week 3 live session. So myself, Vanu, I'm PMR Research Scholar at IIT Hyderabad. So going ahead, in this week 3, Professor Aditya sir has taught you about the double sideband suppressed carrier modulation, spectrum of DSP-SC modulation, signals and coherent modulation. So before that, I should tell you about AM modulation. So as we know, the the expression for AM modulation is what? Is this one? AC 1 plus KAMT cos 2 by FCT. So by seeing here, we can even expand it AC cos 2 pi FCT plus AC KAMT cos 2 pi FCT. So what will be the Fourier transform of this? It will have uh, so it is an interactive live session, so you should be able to answer whatever the questions I'll ask, and think of these live sessions as your a revision modules. So whatever you have studied and just you are just memorizing it with some verbal lectures. So think like that. So since we have AC cos 2 pi FCT, so it will have a delta function at FC and minus FC, right? Or AC by 2 and AC by 2. So can somebody tell me what will be the spectrum of this if you have empty as this one? So how will it look like SF?
Means shifted impulse centered around FC.
Shifted impulse. How it will be shifted?
I think
Yeah.
shifted message spectrum centered around FC.
Yes. Very true. So here you will have this one. So F here FC plus FM and FC minus FM. Similarly here minus Fc plus Fm minus Fc minus Fm. So you have to make sure how this looks like. So double sideband. Here you have two sidebands as well as the carriers. Since carriers are not of any use because it carries only information, so you need to remove it, right? So if you want to remove it, the carrier, so here we'll call it as a suppressed carrier, because you are suppressing the carrier. So you have two sidebands, but when you are don't have the carrier, then it will be called as double sideband suppressed carrier. So in GATE, many questions asked using this spectrum only, like how be able to calculate the power of a type of any signal of AM signal. Suppose AM signal value it is given here as zero point 0.5 and this is zero point 0.5. So and mu is equals to zero point 0.5 suppose. So you will be asked to solve the total transmission power, the total power contained in the AM signal. That it should be AC square by 2 1 plus mu square by 2, right? So here you should be able to understand that AC by 2 is equals to zero point 0.5 and zero point 0.5 mu is given. Otherwise if it is not given, then you will have some methods to solve it. A K can be given or AC can be given or empty magnitude can be given. So you should be able to calculate any problem related to this type of spectrum. And one question is sure short coming in GATE exam. So coming to the next part, whatever the sir has taught you. So double sideband modulation. The sir said xt is equals to AC mt cos 2 pi fct. Here message is mt and a carrier frequency fct. So here no pure carrier is there, where ct is equals to AC cos 2 pi fct. So mt into ct. Here what is it is written. So how you can get this double sideband suppressed carrier? So sir is telling that double sideband suppressed carrier, if the message is having this type of spectrum, then you will have to get. So you have to get this type of in the frequency domain. This one is the frequency domain. So how you have to want to suppress the carrier? So we have some methods to solve it. So firstly, do you guys have any idea how to suppress this carrier? Like think about a physical system. You have the carrier and you don't want carrier at the end. How will you do?
Madam, by passing through a filter.
Yes, yes. So by passing it to a filter, we can have. So basically, one have the understanding that in any communication system, first we have a baseband signal. Then after modulation, we have a band pass filter, band pass signal, because here band of signal is there. Band of signal is passing. So we can use a filter which have a particular frequency, and we can use that frequency to pass our required signal and get the desired signal. So this is what we are practically doing. And in practical scenario also, what is the frequency of the band pass filter? The frequency of the band pass filter needs to be determined very clearly. Band pass filter, so that we can have a proper band pass filtering. So I'll deal with one of the question. So, this time I'm jumping the question so that you will have the understanding, a better understanding. So as K.G. Krishna sir said, the DSP-SC signal is to be can be generated using a bandpass filter. So this was one of the question in the GATE exam. So a DSP-SC signal is to be generated with a carrier frequency of 1 megahertz using a non-linear device with input and output characteristics as V1 is equals to AVI plus BVI cube. So does anybody know about the square law? Square law device? Sir taught in the class, right? So basically, we have methods to get the DSB-AC signal. Some books refer as a square law device. Some has some cube device. Here in this particular question, it was a gate question. If it was a very good question, so I'm dealing here so that you will have better understanding. But here you should know that it should be non-linear. So whenever the non-linear function comes, so the property of x of the function should be there. It can be x square, it can be x cube. Oh, please. Yes, please. So I will actually post this PDF in the link given to you by NPTEL. So if you are not able to see it here properly, then you can see there also, or I think it is visible now. Yeah. So non-linearity will come whenever you have some function of x. So here non-linear device. So here we are considering the function of as this function. So in this question itself, they are given this particular function as a non-linear function. So where Vi is empty plus cos 2 pi fct, and the output of a non-linear device can be eliminated or filtered from an appropriate bandpass filter, the value of f1 is. So they are asking the value of DSP SC bandpass filter value. What should be the f1 value? If we are getting this signal, it should be passed through a bandpass filter. And how we will get, what should be the value of f1 so that we'll get the proper DSP SC signal? So this is one of the way to calculate to get a DSB-AC signal. So let us solve this question here only. So can somebody tell me the approach how to deal this?
Ma'am, I think by expanding we will get the frequencies, and then
Yes,
from
yes.
that frequency we will choose.
Yes, so by expanding this expression, if this type of questions asked in the communication system, actually people lose marks here also, communication system. But if this type of question asked in the communication gate exam, just you have to follow the questions. So here this proper mathematical expression is there. V1 is equals to AVI plus BVI cube. So what is VI? VI is equals to MT plus cos 2 pi FCT. Here VI, BVI. Here I have to draw AC cos 2 pi FCT, pi FCT AC. Because here I am considering VI, so it should be the AC cos 2 pi FCT. But in the question, they are taking AC is equals to 1. So MT plus cos 2 pi FCT. Yeah. So the question is asked about F1 itself. So AC is 1 here. So we have to follow the question itself. So just put it here. V1 is equals to A MT plus cos 2 pi F1T plus B cos 2 pi F1T ACMT plus cos 2 pi F1T plus MT cube. So here you have to identify that which terms will not be able to pass through bandpass filter. So since this one is a not a bandpass filter, it's a baseband signal. The term you have to remember, the baseband signal. So it will have the base here itself. So it will not pass through a bandpass filter. Here only I am eliminating. Will it be able to pass through a bandpass filter? No, right? Because here only F1 will be there. So here itself no. But will it be able to pass through a bandpass filter? So here you have to expand. P cos 2 pi F1T cube plus MT cube. Does anybody is having doubt? Yeah. Yeah, Kurshan. Say.
Yes, ma'am. Ma'am, why cos 2 pi f1t will not pass through this band pass filter?
Because this F1T here, you will have some frequency, right? F1 and minus
Ma'am, this
F1.
f1t is the carrier frequency. This f1t is carrier frequency or something different?
It's a
f1t.
different. It's different. In question, it is asked as a different because generally you have this FCT, but here if it is F1T, then F1 should be greater than FCT. You should have to,
Okay.
because see what happens. FC is some frequency with that is carrying the message signal with a message. So F1 should be greater than FC so that you will have the band pass property. So here it wants
Okay.
pass, and the answer
Okay.
for the value of F1 is 0.5 megahertz. So I will derive this basically, but firstly I should uh, make you aware of the concepts of the DSBSC signal, because I don't know what the sir has taught in the class. But yeah, this is one of the method to get a DSBSC signal. So here, what you are doing, V1 is calculated as AVI plus BVI cube, and then VI is defined here in this itself the question, and you have to follow this particular thing, and you have to get the values that how the F1 should be there for a baseband a band pass filter, so that you will have DSBSC signal. So first we'll see the methods, and these are the questions related to this. Yeah, hello. Somebody's having down. So actually,
No.
this session is very interactive, and the motto of the session is interactive session only. So you please ask out if you have any. Uh,
Uh, uh,
yeah,
Madam,
yeah,
can you just illustrate the difference between a message frequency, which is a baseband frequency,
yes,
and of course we understand carrier frequency FC and F1. What
yeah.
is
Okay,
this
okay.
F1 here?
Sure. So you know this ST is equals to AC 1 plus KAMT cos 2 pi FCT. It's very good question actually. So in practice, what should be the frequency of any message signal? So you know that we have a voice signal of frequency 20 hertz to 20 kilohertz, right? So this is the frequency of audio, sorry. Voice is having different frequency. Audio. So this one is called as frequency of message signal, FM. But when we modulate it with a carrier, so that this frequency will become very high, and it can pass to a larger distance, and some benefits of modulation is there, like less height of antenna is required, or many benefits are there. We can able to modulate it, and we can have frequency modulation, phase modulation, amplitude modulation. For example, if we are considering a frequency modulation, then we will have a frequency of FC plus FM and FC minus FM. Here amplitude will be same. So later you will study about frequency modulation. So sir, frequency FC, here it will be different, and it should be a very greater than FM. So that we'll have the process of modulation. Now it comes the concept of baseband modulation. So since we know that AM modulation has this carrier as well. This is a spectra of the SAT, AMT. Or even if you have the spectrum of the frequency modulation later in your classes, you will find that you will also have carrier along with your modulated signal. This is the modulated signal. So you will have this particular type of filter to have this frequency or particular frequency signal. So here sometimes FC is equals to FM, F1, but sometimes F1 FC not equals to F1. Yeah, it is true that sometimes we require this frequency FC so that we'll have this particular filter and we will get this particular baseband. For example, we require DSBSC signal and with elimination of this carrier. But sometimes we require a different frequency than FC. So that frequency is filter frequency, base bandpass filter frequency, and this is the carrier frequency. So there is some difference between these two. I can understand that you can understand the difference between FC and FM, but you might have the difficulty in understanding the difference between FC and F1. But sir, whatever the desired signal we require, that desired signal allows us to fix the values of F1. What should be the value of F1 to get this particular signal? To get this particular signal. So various signals will be there. Uh, yes, sir. Please. Yeah, question, please.
Ma'am, suppose this is the case of DSB SC demodulation. Okay,
Yeah.
then we have read that for filtering this filter should have its range between it should be greater than FM and it should be less than 2 FC plus FM, something like that.
Yes,
So
yes.
that
Envelope detector. Yeah.
range, that
Huh.
that range, that is only F1 here, that there it was denoted by W. So this F1 and W is the same thing.
No. F1 is the frequency of the filter, right? You are talking about demodulation, and demodulation requires low pass filter. You should understand this. Whenever you require modulation, you will have a band pass filter. Whenever you require demodulation, you will have a low pass filter. And that envelope detector case is having itself has some variation, like it should be greater than equals to 1 by FC and
This
should be less than
F1,
equals to 1 by FM, right? This is
yes, ma'am.
RLC. It was the case of envelope detector. Huh.
Okay.
Yeah, so it is different. So did you understand the difference between these two? So it depends on the signal what we require at the end, at the receiving end.
But madam, F1, is it close to FC in the
Yes,
order?
yes.
Yeah.
Yeah.
So
It-
we know FC is much greater than FM,
Yes,
and
yes.
F1, because it is a characteristic of the filter, it is close to around FC.
FC, yes. It cannot be close to FM because FM is much lesser than FC.
Yes.
Yeah. So I will request all of you to please get the understanding as well as with the physical values. Like sir was saying about FC is much greater than FM. So how much it is greater than? So with what zero values it is greater than? So you should have the physical understanding, the practical understanding, practical perspective as well. So sir has defined this one xt is equals to AC mt cos 2 pi fct mt into cos AC cos 2 pi fct. So xf is equals to mf just in a frequency domain it is this. So how will it look like? Let us draw this. Here we will have mf, have this one, right? So spectrum of DSB-SC signal AC cos AC by 2 MF by minus FC plus AC by 2 MF plus FC. So here sir has removed this fundamental of carrier frequency. So question, let me know how sir has removed it completely.
Ma'am, regarding this modulation of DSB-SC, you are asking.
Yes.
Ma'am, it is quite simple. We have simply multiplied the message signal and carrier signal in the time domain, and due to shifting property of this Fourier transform, the message signal has been shifted, and there is no carrier spectrum present in the final output.
Nice. So basically, what I'm trying to ask, so in the expression of ST AM, You saw that it is AC1 plus KAMT cos 2 pi FCT. So here, if we remove this particular term plus 1, then definitely it will have definitely normal MT into uh, CT, and CT is nothing but AC cos 2 pi FCT. And this is
There is
all we
no pure
required
sine
in
theta.
DSBSC. So you should be able to answer from this particular perspective. So this is A and this is DSBSC. But in practice, how do we remove it? How do we remove it? So that is what the question says. It was having a non-linear device. So we were multiplying this particular sum. We were multiplying through a non-linear device, and we are passing it to a band pass filter, and here we were getting this particular term. But directly sir has written this term. So we will have we will have different perspective from the question point of view. So okay, then this is only this the SPSC if we don't write this one. Now, sir has turned to the demodulation of DSB-SC signal because it is very important. Modulation has not been covered, so no issue. But the demodulation can be carried out by multiplying with a coherently generated carrier at the receiver. So I'll tell you one thing, how to remember this. So you know that how the modulation happens. So you have to remember the modulation, how the modulation happens. So this is MT and this is CT. So modulation happens when you add the signal MT plus CT, and then you are multiplying it with a carrier which is AC cos 2 pi CT, and then you are getting a modulated signal. Here you will have a different block diagrams according to the signal required. Signal.
Madam,
Yeah.
what is CT? What is CT?
Carrier signal.
No, but carrier is AC cos 2 pi FCT, no? I
Yeah,
thought.
yeah. Huh, AC cos 2 pi FCT. Sir, how will you get this AC 1 plus KAMT cos 2 pi FCT? Some summation will be there, right? Cos 2 pi FCT. Means
Okay.
I try to getting this value here using block diagram. Like summation will be there, right? Here cos 2 pi FCT, some multiplication factor MT cos 2 pi FCT. AC will be common if AC goes in. So A K varies and this AC also varies. So basically you will have first a summation, then multiplication with a carrier. Here you can also have AC into cos 2 pi FCT, because AC cos 2 pi FCT plus KAMT, KA cos 2 pi FCT. And when you take this cos 2 pi FCT, CT actually it was the magnitude of AC. So cos 2 pi FCT, then you can multiply at that and you will get the modulation. But how will you get the demodulation? So for getting a demodulation, you again multiply it to a carrier frequency so that you will be able to get a low pass frequency. So what is the fundamental? The fundament of this one is first of all you're multiplying with the cos 2 pi FCT for a modulation, and again multiplying with the cos 2 pi FCT for demodulation, because when you multiply this you will have several frequency cos 2 pi FCT into cos 2 pi FCT. Let us see this particular function. What is the cos square 2 pi FCT? Here you will get cos 4 pi FCT divided by 2, right? So these DC terms correspond to demodulation term. So that's why during modulation we multiply it with the carrier frequency, and during demodulation as well we multiply with the coherently same frequency carrier, so that we will get a DC term, and that DC term will be passed out using a low pass filter. Low pass filter will be situated with a base band, and then you will get a demodulated signal. So let us see using this, using a proper diagram, so that you will have the understanding. But the fundamental is this one, to remember how you will remember how the demodulation occurs. Yeah, yeah, question. Hello.
Madam,
Yes,
uh, just to recap my understanding,
yes, yes.
modulation is adding the signal, right? Adding to the
Yeah,
message.
firstly we are adding the signal, and then
Okay.
we are trying to pass it to a carrier. Then we are, because sir, in amplitude modulation we are trying to modulate the amplitude, right? So some variation in the amplitude should be there. So amplitude variation can occur only by adding a signal. So
Okay.
this, yeah.
So, so the pure amplitude modulation is actually a double sideband, both.
Yes, yes, yes. It should be double sideband. That's why we are removing it after. Sir has not done it properly, but there are some methods of getting the DSB-AC modulation from AM modulation, and one of the method I try to show it using that problem which was asked in the gate exam.
Okay. Okay. So basically, we suppress one sideband to conserve power, right? That's
Yes,
what,
yes, yes.
as I understand. Okay. Okay, man. Right.
Yeah. So demodulation of DSP-AC signal, here only the envelope detection will be coming. So demodulation can be carried out by multiplying with a coherently generated carrier, the same at the receiver. So here we were getting this received DSB-AC modulated signal, where RT is equals to XT cos 2 pi FCT, and then here we are getting this one. So how will we get the demodulated signal? So we are just multiplying it with the demodulation ACMC cos 2 pi FCT cos 4 pi FCT divided by 2 into AC cos 2 pi FCT, same frequency. Coherent means same frequency, this one and this. So further simplifying, we will get this one, and then this particular what DC terms correspond to empty, and that's why we require this, and we are getting this particular baseband signal. So using low pass filter LPF, you will get empty baseband signal, and using some amplitude variation, you can remove AC by 2. So this is what the empty signal you are getting. So what this particular things says. So here, these are called as sidebands, and this is empty, what we had earlier, and this will be having a low pass filter, and this will be having a band pass filter. So you will have some frequency, right? Suppose WP minus WP, and here WL but plus WL. So these two filters differ. So, sir has taken this topic of choosing a low pass filter of suitable bandwidth. AC by 2 empty can be separated from AC by 2 cos 2 pi FCT, which we saw using mathematics, right? So, how this particular W should be chosen. So choose low pass filter such that the cutoff frequency W should be greater than or equals to FM and should be less than or equals to 2 FC minus FM. So how this term came here. So we'll see using a spectra. So W, here we know that W should be greater than or equals to FM by figure, and should be low than, less than, equal, W should be greater than or equals to FM and should be less than 2 FC minus FM. This is because this particular frequency should not collide with this. Or either it can be same, but it will, in practice we should have a guard band, so that we will not have any message loss. So here W should be chosen. But later we will see the envelope detector, which is very important also. So low pass filter blocks this one at 2 FC. Moving to the lecture 15, here sir has taught the double sideband suppressed carrier demodulation, non-coherent demodulation, and impact of carrier phase offset. So earlier we saw that the demodulation can happen through can also happen through a coherent demodulation by multiplying it with a carrier frequency of the same frequency. So how can you get using a non-coherent demodulation? Because it has some benefits. We cannot afford always a FC frequency to get a demodulation as well as to get a modulation. So we prefer non-coherent modulation, demodulation in practice. So DSPSC, this one is the DSPSC signal mathematics diagram, and this is basically a demodulation process, a basic demodulation process, basic building block of demodulation. So you should remember this particular thing. You are getting a modulated signal, which is this is a carrier. So how will you get the value of f? We saw this one, systematic diagram of demodulation process. Here you should have to remember this particular thing. So success of this demodulation technology is depending on the assumption, this particular adaptation. So here we are assuming that modulated phase and this particular phase of the carrier are same, but in practice we don't have. So how this particular offset will affect our demodulation process, and how can we remove this the offset problem? So basically in practice, this is the coherent modulation. No phase offset between the carrier wave in incoming signal and locally generated carrier. This is the synchronous demodulation. So in general we have some different phase offset should be there. So incoming signal, which is a modulated signal, is equals to AC mt cos 2 pi fct, and the carrier generated at receiver is the cos 2 pi fct plus phi. This is the phase offset. So how will you be able to generate it properly? So carrier phase offset phi not equals to 0. The carrier at receiver or local oscillator is not coherent with respect to carrier of the incoming signal. This is the problem statement. I think everybody has watched the sir's lecture. So what is the possible solution for this?
Now we will try to synchronize that receiver fetch.
And how will you synchronize?
There is Costa receiver, Costa's
Yes,
loop.
yes. Costa receiver. Here the concepts of Costa receiver came. So you should know the motivation for each and every concept. So firstly, we were having a normal demodulation process, and then we had a synchronized or the coherent demodulation process. But for that, we require the same frequency at the zero offset. So here the problem of phase offset is considered. Later, we also see the problem of the same frequency offset should be there, because FC should not be always available to have a demodulation process. So here the Costa receiver concept came into the picture. So I think 6:41 it is. So I have questions to discuss also. So we are trying to synchronize it. So firstly, we will just expand the expression of this cos 2 pi fct plus phi. Cos 2 pi fct plus phi. The formula of cos A plus B will be there. Cos A cos B minus sin A sin B. The formula is correct or not? Let me know, please. Somebody. I think it is correct. Cos A plus cos.
Yes, ma'am.
Yeah.
Yes, ma'am.
So you are just trying to multiply this particular formula, and how will you able to get the cos phi value so that you can synchronize with respect to previous one. So cos phi value you will be able to get using this particular thing. And so this one additional factor of phi previously absent in coherent demodulation. So what should be the value of the cos phi? So if we are trying to calculate the power of demodulated signal, which is 1 by 4. The power is basically the amplitude square. So this is 1 by 2 ACMT cos phi. The power of demodulated signal is equals to 1 by 4 AC square PM cos square phi. So it should be less than 1 less than or equals to 1 by 4 AC square PM. Why it is? Because cos phi value maximum value is 1. So how the value of cos phi varies, you will have the proper expression for the Costa receiver. I think it is covered here, Costa receiver, or where therefore important to maintain phase. So one analysis is this, that you have power of demodulated signal. So for example, if the cos phi increases or the phase is increasing between ST and cos CT. CT is carrier signal. Suppose phase is increasing between CT and A. How will it affect the power of demodulated signal? So you can see it is directly proportional to cos square phi. So if the phase between ST and CT is increasing, the power is decreasing. So you have to require a larger phase difference between a demodulated signal and your carrier signal. So this can be a good question in GATE exam, like how the phi and this say phi varies between uh, a demodulated signal, modulated signal and the carrier signal. So, and let me know this cos phi. What should be the value of cos phi? What should be the value of cos phi? Sorry, phi. What should be the value of phi?
Ma'am, it will actually it will depend on the distance between person and this mobile tower.
Uh, See,
It will be variable.
just think about like this, the cos phi is if the offset present at the carrier, and which is in fact in practice it is present. So cos phi, you know that this particular power should be less. Power of the we always want power to be less. The cos phi should be equals to 1, and then phi should be equals to 0 degree. So phi should be equals to 0 degree. Ideal situation. Ideally, phi is equals to 0 degree. But it never happens. So what can be the ways to reduce the phi? One of the way to reduce the phi is to have a amplitude reduction, because we generally see that amplitude is inversely proportional to frequency in terms of the power required, because whenever some power is consumed in amplitude, then less power will be consumed in frequency, and phi is nothing but 2 pi f 2 pi f, yeah, 2 pi f. So phi is directly proportional to f. So if you have power, if you want the phi to be less, then you can add more power to the amplitude side and less power to this one, and you can have less power of the demodulated signal. And this is the practical real life scenario, like how you optimize it. So I'm giving this that perspective. So as phi increases, the output power of the signal decreases, because this cos phi is a non-decreasing function. It's inversely proportional. Sorry. For example, phi is having large value, then cos phi will have a low value. So this is why it is happening. So therefore performance of the receiver progressively reverses. Therefore important to maintain a phase synchronization or phase coherence with respect to carrier wave. And if it is not happening, then you have to optimize the value of phi, and this can be a research problem as well. So moving ahead, carrier phase offset example for double sideband suppressed carrier and demodulation wireless cellular communication with user mobility. So what is happening user mobility? Does anybody know about the Doppler shift or Doppler effect? Okay, so Doppler shift, what is the Doppler shift? Whenever, have you ever noticed like you are going to a particular place and then suddenly you are in a car and that is continuously moving, and suddenly your cell phone is not working, or it is not having internet, or no connectivity if you are talking to somebody. So this is happening because of the handover. You will have but many base stations in a particular area. So whenever a car reaches from this place to this place, this base station handovers to this base station, and this due to which at the boundary the connectivity loses. So I am going to this part because here the user mobility comes in this picture. So here whenever this user is mobile and it is going to one base station to this different base station, and this due to this phase offset will definitely occur, and due to which we face. So how to synchronize it? Let us see with one of the example. So here the incoming signal, which is a modulated signal DSB-AC, as ACMT cos 2 pi FCT into cos 2 pi FCT plus phi locally generated carrier, which after passing a low pass filter we will get 1 by 2 ACMT cos phi. Along with this we will get the cos phi. So extra factor is in comparison to coherent demodulation. So resulting power will be 1 by 4 AC square, because AC by 2 MT cos phi is after LPF. After LPF. So this is a resulting power. As phi or phase offset increases from 0 to pi by 2, the output power decreases to 0. So here phi is increasing, then output power is decreasing because cos phi is inversely proportional to phi. So this resulting power equals to 1 by 4 AC square PM cos square phi, which progressively worsens as phi increases, that is this one, whatever I told. So how does the carrier phase offset arise? So this is the condition, like how where it arises. So output power decreases to 0. Why does carrier phase offset arise? This is due to the distance, as question was saying on the distance factor. But yeah, distance factor come in the picture when you have a different cells, and that you will have a base station, because a particular base station have only particular distance of the circle. So if this is a D, then you will have the coverage of this one only, and if this is a D, this base station will have the coverage of this one only. So for example, base station of user mobile has having the distance D. Then now consider a typical wireless communication scenario. So we need to find out why does the carrier phase offset, or how does the carrier phase offset arise. So we have a base station which is transmitting to a mobile. This one is the base station which is transmitting to a mobile. We can represent this, and this is a transmitter signal. So we are considering a typical wireless communication scenario where the base station is transmitting a signal to the mobile, and keep in mind that mobile user is mobile, moving in the cell or mobile. So the mobile or the base station is not fixed. So propagation delay. So the delay will happen, time is equals to distance by speed. So generally we think about the speed of light, then it is d by c. The propagation delay is a d by c. So here the yt, which is a signal received, actually transmitted, delayed version of the xt, because here you will have addition of delay. So that is what is a tau. A tau is equals to d by c, the signal received at a mobile user. So as a result of this, signal received, that is a yt, which is not exactly xt, but it is xt minus tau, which is not desired. So therefore, the signal received at the user is yt, which is xt minus tau. It is a delayed version of xt. And how can you return write in terms of Fourier transform or in terms of MT or modulator signal? So this one is the modulator signal. Xt is equals to AC MT cos 2 pi fct, and yt is equals to xt minus tau, and then it should be AC MT minus tau cos 2 pi fct t minus tau. And if you write this mt minus tau, since we consider a message signal to be narrow band signal, then here mt minus tau definitely equals to mt, and also message is very slow with respect to carrier. So here the term of phase offset comes. So phase offset is 2 pi fc d by c. So I was telling about d by, I was removing this d by c, but yeah, phi is directly proportional to fc. So the more the fc varies, the more you will have a phase offset. So phase offset is equals to 2 pi fc by d by c. Varying phase offset, which is a function of the distance d of the user. So it is depending on the d. So how you can minimize this? So the minimization comes. So we all know, first of all, we have to, for any maximize or minimize problem, you need to consider a minimum value, where you need to find a minimum or maximum value. So for that, we usually differentiate with respect to t or any required parameter, and just equating it to 0 and just getting the value of this desired value. So del d by dt, since we are transmitting with respect to t, so here you will get the velocity of the user. D by tau d by dt is equals to velocity of the user. So rate of the change of the phase offset is directly proportional to the velocity of the user. So varying distance is resulting in a varying delay, which is resulting in a phase offset, varying phase offset, which is very important. It is directly asked in the gate questions. So moving ahead, hence to avoid performance deterioration, one has to frequently synchronize the phase of oscillator. So you can also get the value of your required if you just del dt by dt is equals to 0, then 2 pi fc by c del t by del t is equals to 0, and then fc is equals to 0, but it is not practically possible. So you have to again differentiate it and check it for what should be the minimum and maximum value. But yeah, you are getting it that the rate of the phase is directly proportional to velocity of the user as well, which was quite obvious also. Hence, to avoid the performance deterioration, one has to frequently synchronize also. So this was all about theoretical part. So yeah, here the Costa's receiver enables coherent demodulation by synchronizing the phase of locally generated carrier with that of the incoming signal. So here somebody proposed this Costa's receiver, so by synchronizing it with the modulated signal, which was the incoming signal. The Costa's receiver actually it enables the current demodulation just by the synchronization. How the synchronization happening, we will see here. So but actually this is arising because in a typical wireless downlink scenario, when the base station is transmitting to the mobile, or mobile is transmitting to the base station, the because the user is mobile, the propagation distance is changing, which results in a varying delay we saw, and that is also resulting in a varying velocity, and that results in a phase offset of the incoming signal with respect to the locally generated carrier at receiver. So we will stop here and continue the subsequent modules. So sir has covered the Costas receiver in the lecture 70. So uh, Let me know the actual formula of the Costas receiver. Mr.
Yes, ma'am.
Can you tell me what is the process to synchronize?
Yes, ma'am, I will try. First of all, we have two demodulation path here.
Yeah,
First
give.
one,
Huh.
first one, first one we will multiply it by the cos shifted by some phase difference, and the second one we will multiply by sine factor, and then using LPF we will get two different terms. First one will be message signal multiplied by cos phi, and second term will be message signal multiplied by sine phi, and then we will simply multiply these two signals.
Okay.
And after multiplying these two signals, we will feedback it back to the that VCO, something voltage control oscillator,
Acha.
and it works like this.
Okay. So yeah, as Kushan has said, so Kirti, are you here? Kirti?
Yes, ma'am. I'm here only.
Okay, okay. So, can you tell me, like, is there any other way to have this synchronization? Yeah, the quadrature one is very famous one. Can you have a other way to have a synchronization?
No, ma'am. Actually, I have gone through only video lecture.
Okay, okay, video lectures. Okay, okay. So okay, nice, nice. So yeah, question as this is one of the way to get at this one, but also we can have some. For example, here what we are doing, sine multiplication and cos multiplication. But whenever if the difference between these two is what 90-degree phase shift, so you can try with any other tangent function like tan, cot, or any other cot. What is others ones? Cosec, right? To have a 90-degree phase shift. But yeah, everyone comes at the cost of sine and cos. Everyone can be written as a terms of sine or cos. So we are basically representing it in terms of sine and cos. So we are just representing the costas receiver using a quadrature multiplication of these two signals, and then again multiplying it and passing it to a voltage control oscillator, and we are getting a synchronization of a demodulated signal, a modulated signal as well as with a carrier signal. So we will not have a phase offset here. So let us see here. XT, which is a DSBSC, which is AC empty cos 2 pi FCT. Then we are passing it to, let us go to the direct this one. So this is the 90-degree phase shift which I was talking about. So you can have this 90-degree phase shift with others one also. I was just asking with the Kirti that you can have other understanding so that you will think about it, because in the future questions they can ask you with other function also, so you might get confused there. So here what you are doing, this one is the block diagram of Costa's receiver. I think I don't need to explain this properly because this is taught by sir very well. So xt, here you are multiplying it with the cos 2 pi of ct plus pi, sin 2 pi of ct plus pi, and then passing it to low pass filter, and the summing it, this you will get a phase discriminator or multiplier. So this is all about the Costa's receiver. This is very important also.
Madam,
Yeah.
in the schematic diagram, where is the output for this Costa receiver? Output signal?
Yeah, here it should be there. Like output of the phase discriminator. Yes, sorry.
Yeah, output. Okay, because the arrow is not there.
Arrow should be there. This
You
one.
can just draw the arrows.
Yeah,
Like
this one,
this.
sir.
Okay,
Output.
okay, okay.
Okay, okay, yeah. So one hour is went, so I think Sir has not dealt with the envelope detector. So everybody has went through the envelope detector, right? I think it is very clear from the sir lecture, so I don't need to discuss it here. I'll definitely jump into the questions. So let us solve this question. First of all, let us remove this. I was telling about the method to generate DSBSC. Just multiply you can get, but yeah, you will have a proper AM signal. Then after that, you have to get a DSBSC signal. So I will solve this question here. Question solving is very important. So I'll again draw this diagram. AC equals 2 pi FCT. Here, properly it should be FCT. Let us draw the diagram that you should not have any doubt.
Madam, the
Yeah.
notation is a adder. Is it a sigma or plus?
Yeah.
Both?
Adder and sigma is same, sir.
Okay.
Sometimes it is written adder and sigma. You don't get confused. So I will write here AVI plus BVI cube. Here MT plus cos 2 pi f1t. Here it is written the VI, so I'm writing it in terms of a diagram so that you can have a better understanding. Or here bandpass filter. You're asking the value of f1. So how will you solve? Suppose this is v1. So v1 is equals to AVI plus BVI cube plus AMT plus cos 2 pi f1t plus BMQT plus cos q 2 pi f1t plus 3m squared t. Here I'm expanding this one. Cube term. This one. This cube term I'm expanding. Space.
Madam,
Yeah.
the message AMT plus cos 2 pi FCT, right? I'm not able to see. Is it?
No,
Is
it's F1T, sir. It is written in the question. It is F1T.
Okay.
So the information is given is Vi is equals to MT plus cos 2 pi F1T.
F1.
The
Okay.
question itself asked the filter. Here value of FC and F1 is same.
Okay.
So you asked me now the difference between FC and FN. So yeah, it
Okay.
depends upon the question. So it is FC and FN same. So I'm trying to solve it. Cos 2 pi F1T plus 3MT cos square 2 pi F1T. So let me know which after bandpass filter which all terms will be there. Think logically, please. So I will tell. Only this term will be here. There.
Yes, 2 pi FCT.
Yeah.
That only, ma'am. Actually, I wanted to say the same term.
Yes. This term will be there. Can you tell me the reason?
Ma'am, frequency of that term is bandpass filter will pass only that frequencies. Other
Yes.
frequencies are like one is message signal is FM, another one is F1.
Yes. So whenever the band pass filter comes now, so question you will having the doubt like whether this term will pass or not. But I'm telling you why this term is not passing because it is not having a message signal. A band pass filter will have a message signal itself as well. So only a impulse function cannot be passed. You have to understand this.
Okay,
So yeah. So
madam, I have
yeah.
one more doubt here.
Yes.
This cos square 2 pi f1t term, it is having two frequencies, right? One frequency will be
Yes,
around
yes, we will
baseband
further
and
simplify it.
second.
Yeah, we will further simplify it. Yeah,
Okay.
we will see it. So, from these terms, as Kirti Thakur said, this one only passed 3mt cos square 2 pi f1t. So, we will further simplify it. How will it look? 3mt by 2, 1 plus cos 4 pi f1t divided, yeah, this one. So, out of this, which term will be passed? Here B should be there, yes? Should remember B. So, Kirti, which term will be passed? These two terms
Ma'am,
are
cos
there.
4 pi fct, ma'am. Cos
Yes,
4 pi fct.
yes, very good, very good. So, this term will be passed. If you are able to solve with this type of questions, then definitely your 4 marks are not gone anywhere in the GATE exam for the communication system. So, here only this term will pass. So, you have to just check with it. So V naught is equals to, I am writing V naught here, sorry, V naught. V naught is equals to 3 MD by 2 B should be there, cos 4 pi F1T. You know that ACMT by 2 cos 2 pi FCT, right? It is the output of DSBSC modulation, right? You have to compare this. So here cos 4 pi f1t को you can write 2 pi 2 f1t and then 2 f1 is equals to fc. Then f1 is equals to fc by 2. And here fc is written. A DSB-SC signal is to be generated with a carrier frequency of 1 megahertz. So carrier frequency is given here as f1 is equals to 1 megahertz by 2. Sorry, I wrote here wrong. So yeah, it is 500.5 megahertz we can write. So answer is 0.5 megahertz. Yes. So have solved correctly. Answer is 0.5 megahertz. So let us just analyze this question once again. So here in this question, a DSB-SC signal is generated. So here a method is given. So this is one of the method IIT professor has thought and written in the GATE exam. So with a carrier frequency of 1 megahertz, which is a FC frequency, using a non-linear device with the input and output characteristics, it is given, and the output of a non-linear device can be eliminated or filtered from an appropriate bandpass filter. So what should be the value of f1? So bandpass filter value should be different, and what should be the value of f1? So here you were asked to find, and we have just calculated f1 should be 1 megahertz divided by 2, which is a 0.5 megahertz. Understood?
Yes, ma'am.
Okay. So moving to this question, NS Murthy Sharma sir went, but this sir was having this doubt in this question, so I again tell with this topic. Okay, whenever he'll see the recording, he should have the understanding. So let us solve this question first. I hope you all know this question. PT is equals to 1. So in the last lecture, my pen was not working, so I solved it verbally. So let us solve it properly. T by 2. So you know that PT here 1 T by 2 minus T by 2, it's autocorrelation. Autocorrelation, can somebody tell me the formula for the autocorrelation? Yes, tell me. It is represented by R. Auto means it's a correlation with itself. Kirti?
Integration from minus infinity to plus infinity.
Okay. That is, you are telling it the expandable form. Just let me know with the convolution form.
Convolution form.
When we will convolve signal bit itself.
Yeah, convolving the signal bit itself with the negative version, right? PT.
Yeah.
Yes, ma'am. Negative.
Huh. So here you will have the even signal. So PT convolving with PT. And you know that convolution of a pulse signal with a coil signal is what? It's a rectangle. But you have to remember this is but t by 2 to t by 2 minus t by 2 to t by 2. So it should be the sum of t minus t and t. Here you will have the slope. If it is having 1, then 1, then 1. So you can write here in terms of this one. So answer is 1. So I think everybody can understand this. So let us move to the next question. Yeah. So we have discussed the topic of AM very often. So yeah, solve this question. What should be the answer? Meenakshi, you are here. Hi, Meenakshi. Dishant, you are here. Okay, then Kirti and Kushid only you will solve this two question. You have the value of power efficiency. You have the value of total power. The expression for the AM signal is asked. Sorry, this is not answer. I don't know. I have to also solve. So please solve. You have
Yes,
to
ma'am.
get the value of A and K.
Ma'am, age 4 by 3 and K age 1 by 2.
A is 4 by 3 and K is 1 by 2. So how many seconds you took to solve this question?
Sorry, ma'am, I didn't hear.
Sorry, I was asking about the time, how much time you took to solve this question.
Ma'am, just now when this question came in front of
Oh,
me, I
yeah,
got
yeah.
the formula.
Yes, very good. So the answer should be B. How power efficiency is what? Mu square divided by mu square plus 2, 1 by 9. You will get mu value. Any value will get. Power is equals to AC square by 2, 1 plus mu square by 2. So you will get the value of AC. Here AC is equals to A. You will get this one. So nice. Moving to the next question. Yeah, this question. If somebody has solved this question, then I will say that you will have the good preparation of gate. So yeah, solve this question. Consider the signal xt is equals to e power minus at ut, where a is greater than 0. Its autocorrelation function defined as this one. Solve this question. It's easy, but yeah, you have the possibility to do mistake.
Ma'am, answer C.
Answer is C. Okay. Kurshid, what is your answer?
Ma'am, just few seconds.
Okay. KG Krishna sir, are you solving?
No, madam, I know it, but it looks like it. I guess it is a three only because tau is not in the picture at all actually because that autocorrelation function.
Yeah. Just let me know the limit of this function. What should be the limit of this function?
Okay.
That is minus infinity to infinity.
Ma'am, the answer is C. Answer is C.
Yeah. Can you tell me the limit of this function?
Yes, ma'am. For tau greater than 0, it is from tau to plus infinity. For tau less than 0, it is from 0 to infinity.
Okay. Do we need to have two limits? No, no. Because here, see, tau.
You take two.
What, Kirti?
Sorry, ma'am.
Yeah. Tell me what you are saying.
Ma'am, actually, my thought is like e raised to minus 8 is multiplied with ut, so that integration sign will be having only positive side from 0 to plus infinity.
Okay.
Actually, I did it with the basic equation formula of autocorrelation.
I thought like you did with that. But see, even if you are solving it with the basic, so minus infinity to infinity, e power minus 80 ut, and then minus 80 minus tau ut minus tau. So since you know that this is in multiplication, ut and ut minus tau. So this ut minus tau will have limit of tau to infinity, right? And ut will have the limit of 0 to infinity. So you will find the intersection of this 0 to infinity and tau to infinity. So the final limit will be tau to infinity. So directly you can put here tau to infinity e power minus 80 e power minus 80 minus tau dt. I will solve, you will get definitely C. So let us solve here also. So is equals to tau to infinity e power minus 80 e power minus 80 e power 8 tau dt. So e power 8 tau to infinity e power minus 280 dt e power 8 tau e power minus 280. You please don't like do like this type of calculation here to here, because if you solve the rough equations properly, then you are having the chance to do less mistakes. So since I was not having this the space, so I did like this tau to infinity 8 tau minus 2a e power minus infinity minus e power minus 2a tau. Here e power 8 tau around 2a e power minus 2a tau. Here we'll get e power minus 8 tau divided by 2a. So yeah, mod you can apply. So you're getting C option.
Madam,
Yeah,
there
yeah.
is another way, right? We can also, because this is a autocorrelation, is a convolution with itself.
Yes, yes,
So,
yes.
so we can do Fourier transform and do later on inverse.
Yeah, you can do so. So here, if it is defined in the question, we can also use that. But yeah, that is also one of the good way to do this. It's auto correlation itself, and then you have to just multiply the Fourier transform of these two, and then just get getting the inverse Fourier transform. So inverse Fourier transform, you might have a difficulty in getting the inverse Fourier transform of the modulus function. So, this is one of the homework I'll try. I'll ask you to do. Please find the Fourier transform of. Let me write here. Very important it is. Fourier transform of mod x and inverse Fourier also. So try to find it. So if you are able to find this one, then you might not have the difficulty in solving with the Fourier transform and then again finding it with the inverse Fourier transform. Why this page is left? So yeah. So let us solve this question. This is also one of the gate paper question. So if AC 1 plus KAMT cos 2 pi FCT is applied through envelope detector, I'll write here envelope detector, then the output of the envelope detector is just a straightforward question it is. Yeah. You all have studied envelope detector by Aditya sir, I guess. Yeah. So let me know. These were the options, and these are the questions which I'm dealing is the mistake question which I did. So please, answer is tick actually. Is AC 1 plus KAMT mod of that? Why it is that? So envelope detector I haven't dealt with you.
Because it is tracking the positive peak.
Yeah. So this was one. It is a diagonal clipping. So here it is a modulated signal. How you are doing the demodulation? You are just passing it with this one envelope detector RS diode, then C and RL and this R, and again it is a low pass filter. This one is the envelope detector. So you are detecting the peak of that. So it should be the magnitude of the this this AM modulated signal. So it is a diagonal clipping. What is it? It is the process is called diagonal clipping. So answer should be B. The peak of ST or modulated signal to have a demodulated MT. Can somebody tell me what should be the diagram for envelope detector? Let me
Ma'am,
know.
diagram of its circuit. Yes, ma'am.
Yeah.
Parallel, parallel, R and parallel C there.
Yes, yes.
Parallel capacitor and parallel resistor.
And here, what should be the low pass filter? What is the diagram of low pass filter?
Ma'am,
Because we know now, for any demodulation, we require low pass filter. So yeah, you should not have any confusion in low pass filter. So please find it out. Yeah, well, I showed it in previous also, but yeah, please. So here, yeah, we will have some questions related to envelope detector. It is a sure short questions came in the gate or your NPTEL exam also. So consider the envelope detector with load resistance RL and the capacitance C employed to detect an AM signal with a carrier frequency FC and the message frequency FM. It is desirable that. Tell me the answer.
Ma'am, the first option.
First option. Okay.
yes, ma'am, first option.
Okay. Okay. Nice. The first option. So one way to remember this is FM is always less than or equals to FC. So 1 by FM is greater than or equals to 1 by FC. So this one is greater than this one. So RLC should be greater than 1 by FC and should be less than 1 by FM. You can write this. Envelope detector, peak detection. So in your analog electronics, you will maybe came across, I think, this peak detection clipper clamper circuit. So it is one of the clamp circuit. This envelope detection is one of the clamp circuit. So you can cross verify there also. So consider an ordinary amplitude modulator signal with a modulation index mu and a sinusoidal message signal MT. The power efficiency of the signal is
Madam, C, option C.
C, ma'am.
yes, yes. So yes, it is here. It is option C, but sometimes you are not directly asked this particular expression because everybody remember this equation. So you just remember ST is equals to AC 1 plus KAFT cos 2 pi SCT. So you have to remember this one. Mu is equals to KA into mod of FT. So you have to remember this one also. So yeah, that is moving towards this question. Yeah, this question please solve. An AM signal is demodulated. I think it is visible. Yeah. An AM signal is demodulated using an envelope detector. The carrier frequency and the messages are message frequency are 1 megahertz and 2 kilohertz respectively. Approximate value for the time constant for the envelope detector is. And time constant here, it is a discharging time constant. How will you calculate? Just let me know the approach.
We should find out time period of FC, like inverse of FC and FM, and the range in between that will be the
Yeah,
discharge time period.
yes. So we will check the options, which options are satisfying, and they will let you. We will just take that answer. So time constant is tau is equals to RLC, which is less or equals to 1 by FC and less or equals to 1 by FM. And sometimes you have this doubt is whether they here it is FM or FC. So you just remember FC is greater than or equals to FM. So moving ahead. Consider the AM signal A1 plus KMT with power and this. I think this question is already solved. This question is repeated. Yeah. The synchronization between phase of locally generated carrier and that of the incoming signal for DSB-SC modulation is achieved using.
Cost of
Costa split.
Okay. So can we achieve using envelope detection? No, it is a method for demodulation, right? For demodulation. And single side modulation, no, it is just a single side modulation you can get using a filter. Super heterodyne receiver. Did you study about super heterodyne receiver yet?
No, ma'am.
Okay, in the later classes you will study. It is very important. Okay. So I think this is the last question. Okay. Consider the envelope detection with the load resistance RL and the capacitors C employed to detect an AM signal with a carrier frequency FC and a message frequency FM. It is desirable that it is very sure shop.
B.
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 Okay. I think 10th question only this time I have taken. No, no, no. This one. Yeah, this was a doubt of NS Murthy Sharma sir also. So, you know what is the answer of this? Consider two signals. It is auto. No, it is a cross correlation.
B option.
Option B. Yes, yes. So, I'll ask you to find the Fourier transform of modulus of x and also prove cross correlation between x and y is equals to xt to y of minus. It is very easy, but you don't have to confuse between these two also. But please find this one. You will have the understanding of Fourier transform. Later, last idea, I'll try to just complete this with a few concepts. So this is important. So if I have the input of it is xt, it is xf. Make sure this small x and a capital X are different because these are two different functions. Okay, I'm taking the Fourier transform because many people are having doubt about this, and this is one of the concepts which everybody should be clear about. So if you have having the input of continuous, time, and aperiodic, you have to answer me whether the what should be the answer in the frequency domain. Continuous, time, and periodic. Discrete, time, and aperiodic. Discrete, time, and periodic. So yeah, tell me. If you have the input of continuous time and aperiodic, what should be the output and what here what is term is called?
Fourier transform first one.
Yeah, yeah. Here, what is it? What will be the output? Whether it will be discrete time, it will be periodic or periodic. You have to answer.
Mine continuous time periodic.
Continuous time periodic. Why, Kirti? If you have the continuous time periodic, the aperiodic, then the output should also be aperiodic, right?
Okay. So,
Yeah. So you just have to confirm with one of the example. So it is a CTFT. It is called continuous time Fourier transform, and the answer is continuous time and aperiodic. So here, tell me, continuous time and periodic.
When it is periodic and it is discrete.
Yeah, your answer is periodic is wrong, but yeah, it is discrete. Why it is discrete? So I'll what is your homework is to solve this mathematically. I'm telling you what is should be the answer. You have to solve it and prove me in the next class. So if the input is continuous time and periodic, so if any periodic signal can be written in terms of Fourier series, and wherever the term Fourier series comes, you'll have a discrete. But yeah, it is aperiodic. You have to prove me. So I'll give you the example of impulse train. Impulse train can be written in terms of periodic functions. It is a periodic function, and it can be in terms of Fourier series, and you have to find the Fourier transform frequency domain and just prove it. The third is discrete time and aperiodic. The answer is continuous and periodic. It is called as DTFT. It is called as DTFT. And when you have the input as discrete time and periodic, it is discrete time and periodic, and it is called as DFT. So have you studied signals and system?
Madam, in
Yeah.
the frequency domain, do we say discrete time or just discrete?
No, sir. We call it as a discrete. Discrete only. Discrete.
Yeah.
Yeah.
The DFT is a discrete
Yeah, yeah,
periodic.
yeah, yeah, yeah. Discrete only. DFT is discrete and periodic. So these four concepts, if you are getting in your mind, then definitely all of your problems related to a Fourier series, Fourier transform will be resolved. So I really request you to solve these four. If you still have doubt, I tell you the answer and input and output. I can also solve it, but I want you to work hard so that you can have the proper understanding of mathematical steps where the terms are coming. So these four are the proper possible inputs, and these four are the possible outputs in the frequency domain. So signals, the term signals comes from this concept only. So you have to understand, go through, and please solve. Yeah, yeah, Birha. Question.
Ma'am, can you suggest some source for us to practice these things? Any
Yeah,
book or any material for this?
Openhead. Have you heard about
Okay.
Openhead?
Yes, ma'am. Openham Bilski, I think it's.
Yes, yes, yes. I read from that only. So you please go through that.
Okay.
Also, madam,
Yeah, yeah.
also, madam, I found Oppenheimer's MIT videos, MIT Open
Yes, yes,
Courseware.
yes, yes. I also saw that. That is very helpful. Uh,
Okay,
so
that is on YouTube, sir.
Yes, yes,
it
YouTube
is
is,
YouTube.
you can search on YouTube and Oppenheim MIT Open Courseware. Yes.
Okay, sir. Thank you very much.
So I'll suggest you to please go through that, and for solving the communication system questions, you can refer to uh, be what was that? So which book you are following?
Simon. Simon Hackins, ma'am.
Simon Hackett. Yeah, it is a BTech course. This book name is referred by, I think, your instructor, right? BTech. But one
Yes,
book is also there already there that is started with B. I'll let you know. Yeah, it is very good. Sir told Simon Hackett only. Yeah,
Uh,
yeah.
Madam, one more thing.
Yes, yes.
Uh, See, currently week 4 assignment is running. Maybe there is a phase lag between your tutorial and assignment.
Yes,
So,
yes, yes. Actually,
uh,
what we are asked to do, we are asked to do one week in one tutorial. So, if you are asking me to go with your assignments, because we are not allowed to solve your assignment questions, it should be done by you only. So, I'll
no,
confirm with
no,
them.
madam, no, madam, that is okay, understandable.
Ah.
But similar questions to assignment, that is better. That will help us to work on our assignments.
Sure, sure,
Yeah,
sure.
it need not be the same assignment, but a similar flavor. Okay.
So I think, sir, I have taken similar questions only related to week 4. You want from you week 4?
Yes, yes, because the current running is week 4, week 3 is over.
Okay, okay, okay. Got it, got it. So I have to, okay, okay. So week 4 is okay. So what is happening now? We have the tutorial sessions have started late, I think, and your course is running fast, a bit fast, a week faster. So okay, then we will try to synchronize it. Will Tuesday Roper IIT? Yes, he should give lecture. So I don't know whether he has given lecture last time or not. But yeah, in the PMRF sheet, he has not. Okay, last week we missed. So did he upload it in the YouTube? Okay, okay, okay. Then I'll confirm it with the team, and most probably Tuesday will also happen. Should happen.
Ma'am, you were telling name of some book, I think,
Yeah, I'll let you
for
know.
signal
Right now I'm
system.
not. Signal system server saying this open head and MIT lectures also there, so you can watch. And for the communication and signal processing, in the company this the signal processing and the Fourier transform Fourier series should be understandable to a very basic level, so that you will be able to solve every questions. So it will be helpful for you.
Is it a BP Lati, madam? There is one book
BP
which is
Lathi, yeah, 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 BP Lathi. I read from this book. This book
okay.
is really very good. So this book is really very good. I must
BP
suggest
that.
that one. Yeah. Thank you, sir, for letting me
Okay, ma'am.
remember. Okay, then I'll end the session, and from the next week, I'll try to solve the questions related to week 5, because I think that time week 5 assignment will be to you, right, sir?
Yes, madam, exactly. Because what happened was week 1 and week 2 together bunched. That's the
Yeah,
reason that we faced.
exactly. Okay, 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 okay. Then I'll solve it into week 5, so that you will be able to solve assignment questions very easily. No issue. Okay, then, and my mail ID is still there. You can ask questions on or through the mail ID also. This is E21RESCH01010 at the rate iith.ac.in. And wherever you are having any doubt, you can just let me know through the mail, and I'll deal with that particular question in the live sessions. So you can you can write this mail. Okay then. Thank you.
Thank you, ma'am.